In the previous lecture, we saw the following bound for establishing concentration bound. We saw that if you can establish that variance of e to the power lambda by 2 c minus ez is less than equal to lambda square by 4 times some constant times expected value of e to the power lambda. If we can establish this, this implied that the log moment generating function of z minus ez is evaluated at 1 by root v is less than a constant log 9, something we got 16 by 9. Okay. That's something we saw, and using this bound, this is sort of a function inequality, and using this bound we can obviously establish a concentration bound. So this part here, yeah, this bound here implies that the random variable c minus ez greater than t is 16 by 9. I just upper bounded by 2 e to the power minus t by root v. That's something we saw last time. And what we noticed was that this particular part, this first inequality, the functional inequality that we need, this can be established by Afrinstein inequality. So we have Afrinstein implies variance of e to the power lambda by 2 c minus c is less than equal to lambda square by 4 times what we were looking for constant v, summation I equal to 1 to n this is my constant v, and times the same expected value of to the power lambda v minus ez. Okay, so that's what we show. That's what we saw last time. And by the way, here this throughout this random variable, the random variable z that we are looking for is this guy. It's a function of independent random variables x1 to xn. Okay, so this particular part of the argument, this is through Afrinstein inequality, and this uses the tensorization property which the Afrinstein inequality gives. Okay, today what we will do is we will basically derive another inequality like this, and what this inequality will do is, instead of variance, it will have some other quantity here which looks very much like variance, and that function inequality will also imply another inequality like this, some bound for log moment generating function. Okay, and this will lead to a very different approach for proving concentration bound, the so-called entropy method. So let's introduce that. So let's introduce entropy and Herbst's argument, which is the replacement of the functional inequality that we saw last time. So remember that variance of y is expected value of y square minus expected value of y whole square. So you can write it as expected value of g of y minus g of expected value of y where g is the convex function g of x equal to x square. A similar quantity can be defined using another function. Consider this function h of x equals to x log x. Then the quantity we are after, the entropy of a random variable x, or let's say y for us, is defined as expected value of h of y minus h of expected value of y. Note that this function h, this guy here, is it's a convex function. Okay, and therefore this guy here is non-negative. Okay, all right. So let's try to express this guy here. So this is the entropy, and what we will show is something similar to what we had earlier. So let me write this lemma and call this Herbst argument. It says consider, so let's fix first. For lambda greater than equal to 0, consider y, the random variable y defined as e to the power lambda z minus expected value of z. So we can consider this random variable. Then and suppose that the entropy of this random variable y is less than equal to lambda square by 2 into some constant v into expected value of e to the power lambda z minus expected value of z. Suppose this is true. So note that this condition is very similar to what you had here, that variance was less than this. We were looking at variance of the random variable y as a factor half here. So you can actually think of this function g as x and square root x, if you like. That would also look similar. Okay. Yeah. So this mod. So if you don't worry about this factor of half, this variance looks very much like entropy. And now the condition we are asking very much looks like this condition here, except that lambda by 2 has been replaced with lambda. So suppose this bound holds. Okay. Suppose that this bound holds, then very interestingly, for every lambda greater than 0, this holds for all lambda greater than 0, then what follows is that for every lambda greater than equal to 0, you have the same bound. You have the sub-Gaussian bound, lambda square by 2v. Okay, so this is Herbst's argument, essentially the generalization of the claim that we have seen earlier. But what's very interesting is that it has given us a way of establishing, if this claim is true, which we'll show now that indeed it is true, then this will give us a way of deriving a sub-Gaussianity bound. Okay. So the random variable z will be sub-Gaussian if you can show that if the entropy of e to the power lambda z minus expected value of z, the central version of z, if its entropy is less than equal to lambda square by 2v times the log moment generating function. Okay, the expected value of the same random variable. Entropy of this random variable is less than equal to expected value of the same random variable. Okay, maybe a better way to write it is as follows. Yeah. Okay. So how do we show this? proof is, again, we have to show a functional inequality that this one implies this one. That's all. So we make the following observation. If you look at, um, let's look at this function g lambda. Then if you look at g prime lambda, what do we know about it? So this is log of, is something we have seen before. So this is the derivative of the log moment generating function. It's 1 by the moment generating function, and you can essentially take the expectation inside the derivative inside the expectation for the smooth function. So you get this to the power lambda 3. Okay. And this guy here, if you look at this guy here, everything actually, just to make my job easy so that I forget about this part, what I first notice is, without loss of generality, we assume that expected value of z equal to 0. Note that since we are centering this random variable anyway, we can just assume this. Then defining g lambda as the log moment generating function of z, of z, we have, what do we have about its derivative? It's the expected value of z e to the power lambda z by expected value of e to the power lambda z. Okay. So what is this guy though? So note that this guy here is expected value of log of y divided by lambda, because y was e to the power lambda z, so maybe I'll just write it this way. Okay. This guy here is 1 by lambda Okay, so we get this inequality. So this implies lambda times g prime lambda is expected value of y log y by expected value of y, which is equal to the entropy of y by expected value of y plus log of expected value of y. Okay, and this guy, if you just, that's how I define things, this is exactly equal to g of lambda. Okay, so rearranging term, what have we obtained? We obtained that this entropy of y by expected value of y is exactly equal to lambda g prime lambda minus g lambda. But now let's look at our assumption. Our assumption for this random variable just says that this ratio is less than equal to lambda square by 2v. That's exactly the assumption we are making. So this implies that lambda g prime lambda minus g lambda is less than equal to lambda square by 2v. That's Okay, so we have this, and therefore our assumption gives this part. So we divide by lambda square and we rearrange term, and this can be seen to in the following. Take the function g lambda by lambda, take its derivative with respect to lambda. The derivative is g prime lambda by lambda minus g lambda by lambda square. Okay, so that's this derivative. This derivative is less than or equal to v by 2. This statement, these two statements are equivalent. So what do we get finally? Now this is true. This is true for all lambda greater than or equal to 0. So you can integrate from 0 to lambda d by d lambda of g lambda by lambda is less than or equal to v by 2 v lambda by 2. And this is true for all lambda greater than or equal to 0. But this guy here, if you see this guy, it's just g lambda by lambda minus g of minus limit x going to 0 g of 0 by g of x by x. Okay, and this is less than or equal to v lambda by 2. That's the bound we get. So the only thing that remains to verify is this guy here. Now this guy here, because of properties of the log moment generating function, this guy here is exactly equal to g prime of 0. Okay, the derivative of g at 0, which for the 0 mean random variable is 0. So this is 0. So we have obtained g lambda by lambda is less than or equal to v lambda by 2. So v lambda square by 2. Okay, that's what we had to show, by the way, because this g lambda, remember, was just an abbreviation for phi z lambda, and we had just centered z. Okay, so we have the sub-Gaussian bound. Okay, so this is a very very elegant method for establishing sub-Gaussianity bound, and it gives you, it says that if you can establish this function inequality for this random variable, then so this is just the log moment generating function. This is just the moment generating function. Show that the entropy of the moment generating function is entropy of this, let's call it the moment random variable. Entropy of the moment random variable is less than or equal to lambda square v by 2, the moment generating function. If you show that, then you have a sub-Gaussianity bound. So we note that this is exactly, I insist this part again, this is exactly what we did in the last class, except that instead of variance, now we have a different quantity which looks very much like variance. Instead of square function, you're looking at this entropy function, and you use that to define some counterpart of variance. So what Herbst's argument tells us is that if we can handle this kind of inequality for entropy of random variables, then we can establish sub-Gaussianity bounds. And so this part is fine. This is the first step. Remember, so this gives a new way of handling log moment generating function. But this is only the first step in our general recipe for deriving concentration bounds. The second step was a tensorization bound. And in particular, we use the Efrenstein inequality to establish the corresponding tensorization bound for this functional inequality. And now what we need is some argument that can tensorize this condition here, that entropy of y is less than or equal to lambda square by 2 times v, expected value of y. And in fact, that tensorization argument will follow from some information theoretic properties, because this function is very much like is reminiscent of quantities like KL divergence that we observe, that we see in the information theory course. I'm assuming some of you have taken that course before. So towards that tensorization argument, so this is the step B. So now tensorization of Herbst condition. Okay. And to do this, we need to do a quick review of the KL divergence, the notion of Kullback-Leibler divergence from information theory, okay, which we'll do now. The Kullback-Leibler divergence is actually a measure of sort of a measure of distances between two distributions. So consider two distributions P and Q on the same alphabet. And such that Q is absolutely continuous with respect to P. That's the notation for it. Q is absolutely continuous with respect to P. This is sort of a heavy language, but we're just borrowing it so that we can keep a bound general. So what does this mean? Q is absolutely continuous with respect to P. So that can mean different things. It's a very general condition. So when both Q and P are discrete, this means that if you look at the support of Q, the set of point where Q puts mass, that's contained in the support of P. So if P of x equals to 0 for any point, Q of x must be equal to 0. This is for the discrete case. In general, it means if P assigns probability 0 to a set, then that implies that Q also assigns the probability to a set. This is in general. This is in general a definition of this. But why does this thing enter? The reason this thing enters is for the following result. If P is absolutely, if Q is, this is something, quick review from something from probability theory, then we can find a density of Q with respect to P such that, so if you want to measure any set under Q, probability of any set under Q, you can integrate over this density. So you can take measure P, except that you have to integrate over this density. So this is that density of Q with respect to P. And this density has a name. It is called the Radon-Nikodym derivative of Q with respect to P. So written as dQ by dP. Okay. So for discrete case, this is just the ratio of the two PMFs. And for continuous case with density, if both P and Q have density with respect to, let's say, the Lebesgue measure, then this is the ratio of those densities. And in general also this guy exists. Okay. So we can define this Kullback-Leibler divergence for any two distributions Q and P such that Q is absolutely continuous with respect to P. If you are very confused about all this abstraction and not very comfortable with it, you can just think of discrete distributions and assume that support of Q is contained in support of P. That's what this condition is. Okay. So we have such two distributions where Q is absolutely continuous with respect to P. Then we can define their Kullback-Leibler divergence. The Kullback-Leibler divergence. This is KL is short for Kullback-Leibler. Between Q and P denoted dQp. It is asymmetric in Q and P, so we start with Q and this base measure P is kept here. Okay, P is the bigger measure here and Q has a density with respect to P. Is given by dQp equal to expected value of dq by dp. This is some random variable, this density random variable, log of dq by dp. That's the definition. Okay, that's the definition of Kullback-Leibler divergence. So when actually let me elaborate this. This is true if Q is absolutely continuous with respect to P. Otherwise, it is just infinite, this Kullback-Leibler divergence. Okay, but let's just put it for this case. Now, special cases. When Q and P are discrete. In this case, the simple formula we have is d QP. Some of you may have already seen it. Summation over x qx log qx by px. By the way, there are two measures floating around here, Q and P. What do I mean by expectation here? When I don't clarify any distribution, it's always with respect to the larger reference measure P. Okay, so this is with respect to P. And for discrete case, this dq by dp is just qx by px, but then you take expectation with respect to P, so you multiply it with px, that goes away, and you get this. Another interesting case is when Q, P are continuous and have densities with respect to the Lebesgue measure. Okay, mu, that's the Lebesgue measure. Then, just like Gaussian or some other two distribution, then this guy is equal to the density of Q log density of Q by density of P. Okay, dx. And this integration here is with respect to the Lebesgue measure. Okay, the standard integration. That's the other example where this has a very concrete form. Okay, so this Kullback-Leibler divergence, why did we introduce this Kullback-Leibler divergence? It is well defined here. Okay. It turns out that we can view our entropy function, in fact the ratio of that entropy to expected value of y, that the thing that appeared in Herbst condition. This thing here. The ratio of entropy of y by this ratio, entropy of y by this. This can be viewed as a divergence, a Kullback-Leibler divergence. And that's what we will see. So lemma let P be the product measure for independent random variables or underlying independent random variables x1 to x. So P is this baseline measure. And f be this function f from x1 to xn to r. So So we consider this measure. Consider q given by. So to define this function q, this measure q, what we will do is we'll just define the density of q with respect to p. You can always do that. And I'll just use this notation x for the vector x. So this is a function of x. What's the density for this x? Suppose this density is, we use a different color, dq by dp of x is e to the power lambda f of x, the vector x, this whole vector x, this is with respect to p. And yeah, so suppose this is my measure. So what does this definition mean? It means that if you want to compute the probability of any set A, that's given by integral of this guy e to the power lambda f x, expected value of under p of e to the power lambda f x, but you have to tell me which measure you use to integrate, and that measure is p. Okay, so it's the expected. Okay, so this is the same as, just to be very concrete, expected value with respect to p, indicate a function of x belonging to A by expected value with respect to p lambda. So you can define some measure q this way, and that's this measure. So this guy has a name. It is a tilting of p. Okay, so it's like you take this measure p and you tilt it with using this function, and it's an exponential tilting of p because you have this e to the power lambda fx here. Okay, so suppose you have this measure, then if you look at the divergence between q and p, that divergence is equal to entropy of e to the power lambda fx by expected value of e to the power lambda fx. So namely what we had earlier, entropy of y by expected value of y. Okay, so this was the quantity that we were bounding in Herbst argument, this guy here. We were saying that this guy is less than equal to lambda square times some constant by 2, and that constant turns out to be the subcausality parameter. Okay, so this actually, no, I should not call this tensorization. I will not be able to prove tensorization in this lecture alone. Okay, let's see how far we go. We want to prove tensorization, but I may stop midway. Let's see. Okay, so what's the proof here? Proof dqp is the expected value under p of e to the power, this is just a definition, dq by dp. Since we have directly defined density, you can verify that q is absolutely continuous with respect to p. If p of some set is 0, then this guy is over, the integration over is over a set of measures 0, so this must be 0. Okay, so then therefore it makes sense. This is equal to expected value under p. This is just by definition, e to the power lambda z. Z is f of x, expected value e to the power lambda z log of e to the power lambda z expected value e to the power lambda z, and this is equal to, you can take this expected value outside into, the first term is and then since log a by b is log a minus log b, so second term here is this part log of, so this is exactly what we had, entropy of e to the power lambda z by expected value e to the power lambda z. Alright, so the proof is straightforward, it's just a re-expression. So very nice. So this Herbst condition that we have seen earlier can be re-expressed in terms of divergence then. Denote the tilted probability measure Q defined above by, so it's P and we tilt P by this. This is a well-defined thing. So you can take any function here, and this tilting is defined as just taking this density e to the power lambda fx by expected value of that. Okay, so if you denote it this way, then Herbst argument is the same as the following. Suppose for all lambda greater than equal to 0, the divergence between lambda f and p is less than equal to lambda square v by 2. Then the log moment generating function one small catch here. I showed this proof with e to the power lambda f, but what happens to the so we have to subtract from it minus e to the power lambda f, right? But note that it doesn't matter. This is exactly equal to e to the power lambda fx minus expected value of fx. That centering comes for free because there's a ratio here. So if you were worried about the centering, it's the same quantity because this cancels from the numerator and denominator. Just a constant which shows up in both of them. Okay, so then therefore Herbst's argument is the same as this bound. This is the assumption, and under this assumption what you get is that the log moment generating function of the centered random variable is less than equal to lambda square v by 2. Okay, that's the very interesting thing here. Okay. In fact, if we go to the proof of Herbst argument, so we observe this guy here. We observe that entropy, but this entropy is exactly equal to this guy, and so we know that this is a divergence, and divergence is exactly equal to this guy, which is this derivative here. So this can be written as, let me summarize that bound here. fact, the proof of Herbst argument, we showed that this ratio of entropy, that's the divergence, this divergence is exactly equal to d by d lambda, so which implies we can integrate over this divergence here. Second, sorry about that. So actually, so what we saw was this is equal to lambda times the derivative of the log moment generating function minus the log moment generating function. This is what we were calling g there in that proof. So you can take out lambda square, and what we can observe is that this is something we observed in that proof, the derivative of this ratio, lambda by lambda, right? So you can see that this is the same as saying that if you have this tilting along f, take this divergence from p, divide by p square, and take this integral from 0 to lambda. This is exactly equal to this by lambda, so I can take this lambda here. That's a very nice formula for the log moment generating function. So it says that the log moment generating function is, I should switch things around, but that's fine. So it says the log moment generating function is this integral from 0 to lambda of the tilted divergence from p by t square dt. Okay. Tilted divergence by t square dt. So you take p, you change it a little bit to get t, to get p tf. This is that the distance between the two, and when you divide by t square, you can think of it as sort of the second order term in the Taylor series approximation of this distance. So you expand this distance and look at the second order term. That second order term, if you integrate from 0 to lambda and multiply with lambda, is exactly equal to the log moment generating function. So this is the gist of Herbst argument. So Herbst argument assumes that this guy here, this term here is less than equal to v by 2, and therefore this integral just becomes lambda square v by 2. Okay. This integral is less than equal to lambda square v by 2. So log moment generating function is less than equal to lambda square v by 2. That's Herbst argument. So to conclude, we have to establish this bound, and where there is this very nice formula. And so why were we doing this alternative expression? Now the point we want to make is that this particular divergence here, it can be expressed, this divergence here, which is the quantity we would like to control, even for our n-fold random variables, we can somehow tensorize this guy, because Herbst argument gives us the counterpart. Remember this lecture we started by saying that Herbst argument gives us the counterpart for this inequality. But now when we prove this inequality, we have to establish this condition for which we use Afrenstein inequality. So what is the counterpart of Einstein's inequality? And by observing that, this divergence here, it looks like the this divergence. Sorry, this ratio here looks like a divergence. We are essentially asking some kind of subadditivity of divergence like Einstein inequality, and that's the kind of inequality which we regularly see in information theory. They are called chain rules, and we in this case need a specific chain rule for divergence, sort of a chain rule. It's a subadditivity part for divergence, which is what we will show in the next lecture. So for now, I didn't actually complete the proof of tensorization. I think this lecture is becoming longer than what I wanted it to be. But so I'll change the title. It's not about tensorization. It is KL divergence and Herbst argument. So we saw the connection between Herbst argument and KL divergence. In the next class, we will use this connection to establish a tensorization for Herbst condition. Okay. Just to summarize, finally, this Herbst condition is saying just this, that the divergence, if the divergence of the tilted guy is less than equal to lambda square v by 2 for all lambda, the law moment generating function is also less than equal to lambda square v by 2. Okay, next time we'll show that this condition tensorizes. See you in the next class.